got it. Yeah.
Okay, so thank you everyone for coming. I am pleased to introduce Sethupathy Subramanian, who is a postdoc at University of Notre Dame. Sethupathy works on computational magnetohydrodynamics with particular interest in high-performance computing. Today, he will talk about using GPUs for accelerating the computation of solutions to hyperbolic PDEs. Sethupathy has kindly agreed to answer questions in the middle of the talk, so feel free to raise your hand and ask questions. Over to you, Sethupathy.
Thank you. Good morning. Today I'll talk about having a high-performance computation code on GPUs. This talk will be mainly focused on the hyperbolic PDEs and how to efficiently parallelize them on GPUs. The motivation for the talks comes from the fact that majority of the modern supercomputers are nowadays equipped with GPUs that are mainly made of NVIDIA and A100 GPUs. And these GPUs are highly efficient. They are very powerful if you use them if you know how to use them. And conventionally, the GPUs are mainly accessed with the CUDA framework, where we have to rewrite all of the codes. But however, in this talk, I will talk about having an efficient and easy way to parallelize the code on the GPUs using OpenACC pragmas. So there are some there are a lot of advantages on the GPU. Also, there are some bottlenecks on the GPUs. The first bottleneck is the data transfer from CPU to GPU. We have to do, especially when we solve the hyperbolic PDEs. So the first one would be to transfer the data from GPU to CPU for each of the time steps. For example, in a MPI computation, in a high performance computing, we'll be having different chunks of the discrete cells will be on different processors, and at each time step, the ghost cell information has to be transferred from one processor to the another processor. In that scenario, the computation is happening on the GPU. After the computation is done, the ghost cell information has to be transferred to the CPU, and then the CPU will communicate to the another CPU with the MPI, and then once again from the CPU to GPU, we have to transfer the ghost cell information to the requested patch. In that scenario, the data transfer is a heavy bottleneck. The second bottleneck would be to have the smaller memory footprint of the GPUs. The GPUs have only about 80 GB at the maximum. The problem is that the GPU 80 GB on the GPU may look bigger, but what's going to happen is that when we parallelize our code on the GPU on about 5,000 cores or thousands of cores, each of the private variable which are private to the core or the process will be replicated 5,000 times or thousands of times, as many times as we use the number of cores. So because of this, the 80 GB RAM is a severe limitation on the GPUs. So this is the second limitation. And the third limitation would be that the GPU is severely hampered by the algorithmic choices. For example, we cannot choose any algorithm we want that can be executed on the GPU, mainly because, once again, as mentioned, the memory is small, 80 GB, and because of that, the cache sizes are small. So it cannot handle bigger matrices just like as a CPU can handle. So that's a third bottleneck. There is also a fourth bottleneck. Conventionally, the GPU codes has to be rewritten in CUDA, but nowadays the OpenACC compilation has become efficient, but we have to do certain things and we also have not to do certain things so that the OpenACC code can run efficiently on the GPUs. So this talk will be mainly focused on the fourth point, how to efficiently parallelize the code on GPUs with OpenACC. So this is a simple representation of hyperbolic PDE evolution with the finite volume method. This is U is the conserved variable, F is the flux, and this is a one-dimensional problem. And LU is the flux, indicates the flux derivative, which will be used for the evolution. And the evolution can happen in two stages. One is the Runge-Kutta update, which happens in two stages, and the another one is the Adair update. It generally happens in one stage. irrespective of the order of computation. Here in the Runge-Kutta, the computation involved with Runge-Kutta itself is very tiny and small. In contrast to the aider, where the aider takes considerable amount of computation. However, for the Runge-Kutta to be used, we need to evaluate the reconstruction subroutine twice. I'm sorry, we need to call the reconstruction subroutine twice, and we need to call the flux constructor subroutine twice. Because it's a two-step process, for both the steps, we need to call them 2 times. For the second order scheme, for a third order scheme, we have to call 3 times, and for fourth order scheme, since it's a 5-stage, we have to call it 5 times. However, that's not the problem with the aider. Irrespective of the order, we call it only once. In this presentation, I'll also discuss how I discuss and compare Runge-Kutta scheme is efficient for GPUs or aider scheme is efficient for GPUs. And that will also be discussed in this talk today. Okay. Now, I'll look into the algorithmic choices that are most considered efficient for the GPUs. Before I start discussing the point, I want to mention that these limitations of the algorithms comes mainly from the practical limitation of the GPU, that its cache size is small, its memory is small. As the day progresses, the GPU memory and the cache sizes are going to improve, and these limitations may not remain as a limitation anymore. However, these are the present limitations that we faced when we want to parallelize the code. First one is the reconstructions. We use a Vino reconstruction because we only use the zone-centered variables, and we only transfer the zone-centered variables from GPU to CPU. If you use the HVino or DG schemes, we also have to transfer the slopes, higher order slopes. For example, for the second order scheme in 3D, we have 3 slope terms, X, Y, and Z. For third order, we'll have about 10 slopes, right, and for fourth order, we'll have 20 slopes. So if you use HVino or DG, the amount of data that will be transferred from GPU to CPU is huge. So we resort to use the Vino scheme for now. And the second one is the reconstruction part, where we have the we always do the reconstruction with the conserved variable, but not use the characteristic variables, because the characteristic variables required a eigenvector matrix. It may be one matrix on the CPU, which can be computed locally. But when it comes to GPU, when we parallelize, that matrix has to be replicated, will be replicated by the GPU as many thousands of cores as it has. So this will put a severe limitation on its cache memory. So the speed up will not be much. The computational is still possible. The speed up, the gain will not be much. And I talk about the time stepping. We can use Runge-Kutta or aider, but I'll talk about this more. Why we need to choose aider, not Runge-Kutta, but that choice can be discussed. Why which can be chosen. This will come inside the presentation. And fifth one is the Riemann solver. As I mentioned before, the matrices are difficult to handle within the GPU because of the limited cache memory. So we resort to the simpler HLL Riemann solver. So as we mentioned before, all of the astrophysical codes which are used in production have been developed for decades. Be it developed in Fortran, C or C++, all the commonly used astrophysical codes like Pluto, Zeus, everything is developed for decades. Now we cannot simply go ahead and rewrite all the codes for the GPU with the CUDA. So that's nearly impossible task, and we are going to introduce new errors if we do that. So we do not want to do that. So we come up with the alternate. We have to use the alternate option. That's the OpenACC. And in this presentation, I'll discuss how we can efficiently parallelize the code with OpenACC. So this is a general structure of a hyperbolic PDE solver. This is a pseudocode for a hydrodynamics code, which has very minimal elements represented. I'll talk about the non-colored versions first, just to introduce what we are doing. Nx, Ny, Nz are the number of zones, and U is the conserved variable which carries with 5 indices. The first 3 indices are for the X, Y, and Z cells, and the fourth index 5, which carries the number of components, that is density, X momentum, Y momentum, Z momentum, and the energy. And the fifth one is the first one carries the zone-centered value, and 2, 3, 4 are for X mode, Y mode, and Z mode. And the fifth one is for the carries the time mode, which we will use it for the adder computation here. And then the color variable is U skinny. It has one dimension that is less than the U. And for this particular pseudocode, we choose the U skinny to be holding all of the zone-centered values of U, but it can be code specific that we can discuss later. And there is a du dt component where we use the time of where we store the time of date. And then there is fluxes, X flux, Y flux, Z flux for coming from the X phase, Y phase, and Z phases. And then these are some of the scalar variables, dt, dt next. CFL is the CFL number, dx, dy, dz are the cell sizes, indicate the cell sizes. And then we call the initialization routine as we do. It initializes on the variable u skinny, that is only the zone-centered variable. And then we do the we go to the time stepping routine as usual. First, we do the impose the boundary conditions, and then we call the reconstruction routine, and then we call the predictor step, that is the adder step. With the predictor step, we get the fifth mode of the U. We use that to compute the zone average and time average fluxes. I'm sorry, phase average and time average fluxes. We use these fluxes to calculate the du dt. And then we use the du dt to update the U. And also we compute the next time step dt in this subroutine, update U and time step. And then we use the new dts at dt, and then we do the looping once again. So this is a general common structure of any hydrodynamics or hyperbolic PDE solver. Now I'll talk about the ACC pragmas that we use. The first one is the data create. In data create, we tell the GPU, create the memory for these variables, U, skinny, U, du, dt, flux, and all these variables, which means these variables are going to reside on the GPU as well as on the CPU memory, both. So when we tell the GPU to do the computation on the GPU, it's going to access these these variables on the GPU and do the computation. If you do not tell, it's going to do the computation on the same variables, but it will be doing it on the CPU. So we should be aware of that. Okay. After that, after the data is created, we call the initialization subroutine. This subroutine is incidentally done on the CPU. So what we do, it is done on the CPU. The U skinny is assigned on the CPU. Now we have to update the same variable on the GPU memory. So that's why we call the ACC update device. It will update the U skinny, dt, CFL, dx, dy, dz on the GPU. Now we have these variables available on both CPU and GPU for now. And this is done, but I'll go to the next step. And then we transfer the U skinny to the U on the GPU itself. And then we do the rest of the computation. At the end of the computation, once the U is updated, we take the updated U skinny and then put it back onto the CPU memory, that is host. After this, the steps are not shown here. After this, the MPA communication will be done because now we have the updated U on the CPU. Now the MPA communication can be done. So that's the general structure we followed in all of our, we have done the test on hydrodynamics, magnetohydrodynamics, and electrodynamics codes. This is a general pattern we followed. So this is what, I'll not explain all of the subroutines. I'll explain about about 4 or 5 subroutines which have different kind of functionalities. First, I'll talk about the U skinny to U functionality, where we transfer the zone-centered values to the U itself, so that once it is transferred, the next call is for the boundary conditions and the reconstruction subroutine, where we do it on the conserved variable U itself. Here, we simply, if you look at the do loop, we simply assign the zone-centered value from the U skinny to the first mode of the U. For this, we have these OpenACC pragmas. First, I'll talk about the ACC parallel. When we say ACC parallel, and then at the end, I say ACC end parallel. Within this region, all of these computation will be done on GPU in a parallel way. That's the instruction we are giving to the GPU. And then we describe the vector length because that is the length of the vectorizable operation that can be done on the GPUs. And present means we tell the GPU these variables are already present on the GPUs. And these variables will be shared just like in OpenACC. In OpenACC, we say shared. Here we say present. That's the difference. And then we have the we collapse all the three loops at once. That's because since GPU has thousands of cores, if we do not collapse the three loops, we do computation on two loops, and then we do different types of parallelization. In our experience, that's not efficient. But for these applications, we always do the collapse tree. We always collapse all three loops. This ACC loop indicates we have the loop here, and then the gang vector indicates there can be three different kind of parallelizations. One is gang, the other one is a worker, and the other one is a vector. Vector is the lowest level of parallelization. We tell the GPU that we want to parallelize till the lowest level of parallelization, starting from gang to vector. The worker is an optional, so I did not include that. And we say that all the three loops can be run independently. That's why there is an independent keyword. This is important because then the GPU will run very fast. The execution will be very fast because we give specific instruction, it will be very fast. The OpenACC pragmas are guidelines for the GPU. It's not like CUDA, it's not a specific saying. So if the guideline is stronger, it will be the parallelization speed will be much stronger. That's why we say independent here. We'll give the GPU to go ahead and independently do it. Otherwise, it will try to be correct, which means the speed will be lower. The ACC parallelization will not be efficient. That's the problem. And then, yeah. Okay, that is the question. So generally the length that is chosen is about 64 or 128. That depends on the number of vectorizable cores available on the GPU. Incidentally, the 64 seems to have a higher speed up for our application. We stayed with the 64. And in discussion with the NVIDIA people, we asked the same question too. They said, whichever works better for the code, you stay with either 64 or 128. That's the option we got for A100 GPUs. So that can be discussed. Sometimes people also, you can use 32, but generally it is in the multiplicity of 16, 32, 64, or 128. So if for example, since the question is asked, if the vector length is 64, and then only 64 process will be vectorized. Vectorization means, I think, I'll just say what is a vectorization. Vectorization means you have array A and array B, and then you want to add array A and B to array C. So this operation will happen in one clock cycle. That is a vectorizable operation with multiple cores doing at once. And we have the parallel private variables that are declared here. IJK are the private variable for this simple loop. This is a general structure where we say what is present on the GPU and what is private on the GPU. And then we ask the GPU to do the computation. This is a very simple structure for this. Now I'll move on to the next subroutine. I'm not going to discuss the boundary conditions because that's that is more similar to this. So we'll look into the limiter subroutine where we have an outer loop in addition to the triply nested inner loop here. So in the outer loop, depending on the value of n, the component, if it is rho or momentum or energy, we are going to change the compression factor for the limiter and change on limiter. In this region is never been indicated to be a GPU region. So this operation will definitely happen on the CPU. Once this happen on the GPU, we have to update on the device using the update device pragma. And before we update the device, this variable has to be present on the device. So I use the pragma called ACC data copy in. We can also use ACC data create. It is same as ACC data copy in, except in data copy in, it is going to copy the whatever value available on the GPU, its CPU, and then it will copy it to the GPU. It will do both operations, data create as well as update device combined into one, that is data copy in. And once it is updated on the device, this is a scalar variable, and it is common for all of the triply nested loop operations. So this is used as a shared variable along with U. And then we have the local variables IJK, S1. S1 is a slope 1 and slope 2, which we use it to compute the MC limited value here. Here I updated only the X slope. In a similar way, we can also update the Y slopes and Z slopes. And at the end of the parallel loop, I indicate the ACC in parallel. Also, for the data copy in, I'm also having an end data, which means the data that is copied in will be deleted at the end of this subroutine call. If you do not want that, we can use a data create here that will sustain till the end of the code execution. And the third one is a predictor subroutine. Here, this can be a repeatable procedure for any triply nested or any do loop codes, because the work that we need to do is put it in the subroutine called predictor zone wise, which will operate on each cell or cell wise, which will operate on each cell. And this is the working subroutine. This is the worker subroutine for this triply nested loop. This subroutine will be called in a sequential fashion on each of the by every core of the GPU, and it will be executed in a sequential fashion. So this has to be indicated to the GPU at two places. One, within the parent subroutine, the predictor subroutine, we say that this subroutine, predictor zone wise or cell wise, will be called in a sequential fashion. We have to indicate to the GPU here, as well as we have to indicate within the subroutine of the predictor zone wise. ACC routine C. This has to come after the declarations are done in this routine seek, and this routine seek has to be done. I'm sorry, I think I lost the point. Yeah, okay. So this has to come right after the subroutine is mentioned. So after this ACC routine seek will have the declarations of the variables, etc. So here I want to mention some of the bottlenecks that we faced, because this is a one shop. This can be repeated for it. Yeah. The call to the predictor zone wise, whatever we write inside the zone wise subroutine, that will be done in a sequential fashion. Overall, for every cell will be done for let's say you have 10 cells, and each cell will be done on each of the cores in a parallel way. But what we do in a parallel way, that is in a sequential fashion. So for especially in the higher order Aider schemes where we have very big matrices, and especially when we have a Aider implicit schemes where we use it in electrodynamics because of the stiff source terms, we may even have a small matrix inversions. All of this can be done within the sequential subroutine, but the main bottleneck is if the matrix sizes are larger, the cache size is going to be very limited. So the speed up will be very limited. That's the main problem. And second practical limitation is that I don't think many people use Fortran, but I'll say that if you use Fortran, we are going to pass the array sizes nx, ny, and z or a matrix size of 16 cross 16 as a variable from at the function we call it interface, at the function interface. So when we do that, this subroutine can be in a different file. So when we compile that file, generally, the compiler does not do the array size. It doesn't matter if you do the CPU, but for the GPU, the compiler has to know the array size within the sequential subroutine. So always a number should be there. If we cannot put the numbers, we can put this a directive like in a hash define, and then that during compilation, the array size will be known. So the compilation array size has to be known. Because I'm stressing this because the compiler will not complain about this, the NVIDIA compilers. NVIDIA compiler many times will not complain about many things. That is another problem. But compiler will not complain. Only way we will get to know it, sometimes the code will not be executing correctly. Sometimes what's going to happen is that the code will be running very slow. And even in C, if you write a C code, the variable length are permitted now. Not in C++, I think, in C code. So this practice is not possible when we do the GPU computation in a sequential fashion, especially. So this is those two are the limitation. One is the memory, amount of memory available. Another one is even if the memory is accommodated, the cache can be limited. So the speed up will not be much. Okay. Now let's focus on the next subroutine. That is one example. I'll talk about it only the X fluxes, how we make them. The situation is very similar to the previous case where we have we say U and flux X are present. Okay, I want to recall that we say U and flux X are present, but in this subroutine, the U and flux X are not moved to the GPU. It doesn't matter because in the main code, we actually did a data create, and then we said U, flux X, flux Y, all of them are created on the GPU. So that's the reason we say U and flux X are present here. And then we have the pointwise, the zone-wise private variables I, J, K left from the left side of the face, the UL from the left side of the zone from the face, and the UR from the right side of the face, which on which we are computing the flux, and we compute the flux with the pointwise or a cell-wise subroutine. It's very similar to the previous case where we have a Riemann solver. We have to declare the routine sequence here, and then we have to declare here ACC routine sequence. Once again, here if you use the if you use the Riemann solver with the eigenvectors and those HLLI and HLLC Riemann solvers, then the cache performance will not be optimal. But this trade-off can be application specific. If the application requires HLLC, then we have to use. There is a trade-off involved in the speed up. Okay. So this has a small amount of variation compared to the other subroutines, mainly because we want to compute the delta t for the next time step from the getting the speeds from all of the cells in the computation domain. In this scenario, we want to minimize the variable dt next, that is the delta t next. We want to minimize by getting the information from all of the zones that is involved. Here, the computation cannot be run independently under parallel fashion because the dt next depends on the dt next from the next zone, from all of the zones. So that has to be indicated to the OpenACC by saying that reduction min dt next. This is enough. The situation is very similar to OpenMP, and OpenACC will take care of itself. That is all. And once again, the dt next is assigned on the GPU as some much larger value before we minimize, and it is updated on the device with the ACC update dt next. So that has to be. So sometimes if you do not remember to do the update device, the compiler will not complain. Because why? Because we created the dt next in the dt next is already present on the GPU because we did the data create. So it will not complain. So we have to be conscious about updating the device on the dt next. So this can be a potential buggy situation when you do the coding. Okay. So these are all some of the things which I wanted to discuss. And now I'll discuss about the speed up that we got from different orders. And in the next slide, I'll talk about the comparison between Runge-Kuttab and Aider schemes when you want to parallelize on GPUs, how much speed ups we can get. The first one we can focus here is that the CFD is hydrodynamics, MHD magnetohydrodynamics, CD is electrodynamics. We consistently had higher GPU performance when we go from lower order to higher order. From second order to third order, if you see the GPU speed up is much higher, because once the data is moved to the GPU, we perform a lot of computation on the GPU. The GPU is going to perform much faster than the CPU. We are going to have much higher speed ups. But that situation we did not get for the fourth order. I'll discuss in the next slide why we do not face. Same situation is has happened for the MHD also. So third order performs better than the second order. But for the CED case, that did not happen. We have a second order and third order and a fourth order, which has a much higher performance. However, on an average, the electrodynamic case has a much lower speed up compared to CFD or MHD. What we identify is that we actually timed each of the subroutine, how much each subroutine takes on the GPU to be computed. What we found is that the Aider subroutine taking a very substantial amount of time on the GPU, and that this is the bottleneck for the speed up. That's what we identified. We can see that for the second order, this is all of the computation time that is taken by the GPU for a different number of zones. And the purple region or a violet region, that is the time taken by the Aider scheme. This is for second order hydrodynamics case, third order hydrodynamics case, and fourth order hydrodynamics case. We can see that the number of computation time taken by the aider has only risen to a much larger extent. As we know that the GPU can do any amount of computation in an efficient way than a CPU, but what it cannot do efficiently is that because of its limited cache memory, it cannot handle larger matrix sizes efficiently because it has a smaller cache memory. Because of that, we face higher execution time on GPUs for the aider scheme. It remained a bottleneck. The same situation was replicated on the MHD as well. This is MHD second order, MHD third order, MHD fourth order. The yellow color is the total execution time, and the purple color or the violet color region is the time taken by the aider scheme, which is much larger for the fourth order. So the situation is like this here. But for the computational electrodynamics, we always have a stiff, so most of the times we can have a stiff source terms. So where we have an implicit aider that is much more computationally demanding than the aider that we used in the hydrodynamics or the MHD. So there, the computation time taken by the aider is already significant in the second order. And again, once again, more significant in third order, once again, more significant in fourth order. Because of this reason, we could not get a higher speedups for the CED case. I'll go back to the speedup curves. We can see that the CED speedup curves are much larger, about 40 times, 60 times speedup we get compared to 100 times speedup that we get from CFD or MHD case. The very interesting thing is that the fourth order has become more efficient on GPUs. That is unexpected. What we predicted is that from the experience, for the fourth order with the CED, we have a matrices are much larger. We think this happened because even the cache sizes of the CPUs are unable to handle. The cache performance on the CPU also came down. So that's why the relative speed up on the CPU to GPU has improved for the fourth order. That's what we think. Okay, so we execute the same code on a single core on the CPU, and then we compare on a GPU where we actually parallelize. So this comparison is for one core CPU with whole of the GPU. I'll also provide a comparison for multi-core CPU with GPU for the MPA after a few slides. Yes, the fourth order, the denominator. Yes. So that we did not expect, but that has happened. Okay. So these are all the practical limitations that we faced while doing the GPU parallelization with OpenACC pragmas. As we can see, the OpenACC pragmas are really simple. If you follow this, we call it a winning algorithm. There could be many winning algorithms. If you follow the similar strategy, like parallelize the 3 loops, collapse the 3 loops, and explicitly say it's independent, and then you follow these steps. If you follow these steps, having a sequential subroutine with smaller matrix sizes or no matrix sizes, you can easily get a 100 times speed up with a minimal work. Especially, for example, I have seen your execution of some of the some Mark 10 runs, though it is 2D, it is a very high resolution run. It would have taken how long it took? Okay, 40 threads you did in 2-3 hours. Okay, so that is very efficient. I was thinking it took some days. I'm sorry. Okay, so yeah, 2-3 hours is tolerable. Yeah. Sometimes if you are going for a very high resolution 2D run that cannot be parallelized on GPUs, it can run much faster. So so far I discussed about the limitations on the aider scheme. Now let us look into how much Runge-Kutta can improve the situation in this scenario. So these are the speedups. Here I have provided for the number of zones that per second for the aider scheme and the Runge-Kutta scheme. What we do not show here, but we have shown in the paper is that the Runge-Kutta scheme speedups are more than 100 times. They are more than 100 times faster than aider code for second order, third order, as well as fourth order. They are more than 120 times. Sometimes I achieve 120 times speed up, or 150 times speed ups also achieved for some of the codes. The speed up is much higher. However, the main bottleneck comes from the Runge-Kutta scheme is that Then since we have to call the limiter subroutine or the reconstruction subroutine as well as the flux calculator subroutine twice for the second order, thrice for the third order, and 5 times for the fourth order, these repeated calls hamper the overall zones per second of the Runge-Kutta schemes. The dotted lines show the Runge-Kutta scheme zones per second, and the solid lines show the zones per second that is done with the aider. The speed up that we obtained from the Runge-Kutta scheme is substantial, very good with the OpenACC. However, the zone, if you compare the direct zones per second, the aider schemes still performs better, though the speed up is about 80 times or 60 times in cases. So that's the comparative study that we did with the RK methods and the aider method. We did not do the comparison of aider versus RK for the CED case because the aider that we use is an implicit aider. The RK that we use is always explicit, so we do not want to compare. So that's why we did not have comparison. And this is simply an accuracy study that we did on the GPU just to ensure the code is running properly with the correct values, because we do not face new round of errors with the GPUs. We have the same accuracy. We got the L1 errors. Also, we computed once again on the GPUs. We got machine accuracy. This is just a check. Okay. So far, I have discussed about the parallelization of the codes. Now I'll discuss about the practical code that we use. Okay, since if anybody has any questions. Yeah, sure.
When you use implicit data, can't you reuse the same matrix?
Yes, we can, exactly. When we use implicit data, we can reuse the same matrix if you do it on the CPU. And that is true for any of the sequential called subroutine. You can have a small matrices, 30 cross 30 matrix, even a small matrix. The problem is when you say it's a private and it is going to be vector parallel and it is going to be replicated. The private variables are replicated on the GPU memory so that it can run at once. So that is the main problem, because this replication causes like 5,000 copies of 30 cross 30 matrices, right? So that is the main problem. That's the main bottleneck that we faced. How many zones are getting executed per second? That's what we calculated. We achieve that. We take one time step, and then there will be a certain amount of time it will take, and then we have the number of zones, and then we just divide the number. That's it. Okay. Now I'll move on to the this practical code that we used in the astrophysical application for the simulation of. So far, we used it for the simulation of massive star winds. It can be used for any general spherical object, astrophysical simulation objects. We sectionalize the cube into 6 divisions. This is a cube. We call it a This is called as a cube sphere meshing of the cube. I'm sorry, the sphere. We have about 6 different blocks like this. The only 4 are shown here. The front one and the back one are not shown. We use this. And each of the blocks can be sectionalized as many times as we want for the MPA communication. Subdivided into 4 or 9, or it's a square value because we divide as a equal segments. That's how the code is constructed. So we do this. We did this, and then we checked this code is parallelized on the GPU to run, and then we check the speed up, how much of speed up that we get on the GPUs. This speed comparison is done with one CPU with one GPU. The CPU that we compare is the AMD, I forgot its name, CPU, which has 64 cores. That's a very modern CPU. And the GPU we compared is the 80 GB RAM A100 GPUs. So when we used 12 CPU processors, 24 CPU or GPU, 48 CPU or GPU processors, and 96 CPU or GPU processors. We did the speed comparison. This speed comparison can be done in 2 ways. One, we can parallelize the code completely on OpenMP with smaller patch sizes, or we can choose, for example, for the 12 processor run, we divide the Q-sphere into 12 patches, and then each of these patches are parallelized on the CPU with OpenMP. So this is the speed up that we get with OpenMP plus MPI. This is the speed up that we get with only MPI. This speed up is compared with the GPU. So we get about 5 times speed up effectively with OpenMP and MPI combined together. And then with the MPI, the speed up keeps increasing as we increase the number of processors. That's because the amount of communication is going to be huge. Because 96 into 64, that many patches will be there, and that many patches has to be communicated for each of the times too. So this completes, okay, I'm sorry, one more slide. So we also did the scalability study for the code. We found that the code is scalable from 12 GPUs to about 96 GPUs. This is ideal scalability for the GPU, and this is the practical scalability that we obtained with the GPUs. Thank you. Anyone have any questions?